Welcome back to Chem 4300. In this video, we're going to continue looking at the physics of traveling wave packets. Now, imagine you had a very long rope and you grabbed one of the ends of the rope and you just jerked it up and down really fast, just once. And when you do that, you would create a little wave packet that would travel down the length of the rope and continue on. Now, if the rope was fixed at some point, eventually it would hit the wall and it would bounce back at you. But for our purposes here, let's imagine a rope that just goes on forever, but it's held nice and tight here as you make this wave and let it propagate down. Now, in the previous video, we learned how we could decompose a wave in terms of sinusoids. And in the last case, we were looking at waves with boundary conditions, so like the standing waves of the string of a violin, for example. But in this case, we're talking about a wave that's propagating on a string or medium that has no boundary conditions. Now, we can still do this decomposition in terms of sinusoids, but we're not going to be able to use the Fourier series, which would assume a discrete set of wavelengths, but we have to do something called a Fourier integral. So this is going to be a generalization of the discrete Fourier series in something called a Fourier integral transform. So the general idea is that we replace that summation with an integral, and now our wave function, as a function of position, gets multiplied by e to the I kx. Now we're going to switch to using complex number notation. So we're going to multiply it times this sinusoidal oscillation and integrate it over all values of x to get the wave function represented as for a given particular wave number, k. Now we're going to do this integral analytically, so we're going to have an expression for all values of k. So what we've done, in a sense, by doing this integral is a type of coordinate transformation, transforming the wave function as a function of position into the wave function as a function of wave number. Both are equally valid, both contain exactly the same information. They're just two different representations of the same wave function. And conversely, you could go backwards. In other words, if you had the wave function entirely in terms of wave number, you can transform the wave function back to the wave function in terms of position with this integral here. So you notice the difference in these integrals is just the sinusoid here, which is e to the I kx. Here it's e to the minus I kx, and here it's e to the I kx. So there's a difference in the sign there. And that's what we call the Fourier transform and the inverse Fourier transform. Okay, so what we're going to be doing then is we're going to be describing our wave moving through space either in terms of a wave as a function of position or a wave as a function of wave number. Both are equally valid, and the connection between those is this thing called the Fourier transform. Okay. Now you may have noticed over here that our integral is going from negative infinity to plus infinity, so that's the range of wave numbers. And this introduces sort of a new idea here. So generally speaking, a negative k is not associated with a negative wavelength. That doesn't make any sense. But rather, when we use a negative k, we're saying that this is a wave traveling in the opposite direction of a wave with a positive k. So we're giving k a greater role than just wavelength. So wave number now not only contains information about the wavelength, but the sign contains information about the direction that the wave is traveling. Now, if you think about a wave packet in terms of decomposition of sinusoids, this is sort of a simple example here. If I imagine a wave packet that looks like this, I could construct that wave packet, this wave which is localized in this region of space, by performing a summation over a number of sinusoids that extend from minus infinity to infinity in terms of position here. But they're all arranged so that at the position where the wave packet is maximum, all of these sinusoids are in phase, and outside of this region, they become out of phase, and so they interfere destructively out here, and as you see, they only interfere constructively where the wave packet is localized. So that's sort of another way of just sort of imagining what we're doing in the Fourier transform. What we want to do with the Fourier transform is we say, given this, what is this decomposition? What are the different wave numbers and amplitudes that you need in order to add them together to get this wave packet? So let's take a look at an example of how we would do a Fourier transform, work out the integral and get an expression for the wave function as a function of wave number. So let's take a wave function as a function of position, excuse me, and I'm going to use an example of a Gaussian wave packet. So just imagine a simple Gaussian shape which is on our string and it's propagating forward in space. And this is what it would look like as a function of time. Now I'm just going to be looking at the wave packet at some instant in time. So let's call that time 0. So I'm going to set t equal to 0, and I'm going to write my wave function f of x t equals 0 and put it into the Fourier integral. So I'm going to take this guy with t equals 0 and put it into the integral. And this is the integral I want to calculate if I want to get the wave function in terms of wave number. Right? Now, what you see is, okay, this looks like a pretty, kind of scary integral to do, but we can actually break this down and make this integral go much quicker than you might expect. So first of all, we're going to use the Euler relationship, which tells us that e to the I, or in this case minus I kx, can be expanded out as cosine kx minus I sine kx. And then we break this integral up into two parts. So here's the cosine part, and here's the sine part with the imaginary number there, I. And when we look at this, then we can also use our sort of understanding of even and odd functions to decide which one of these integrals are going to go to 0 and which one aren't. So what we see is that this side, this integrand, is an even function, and this integrand is an odd function. And since they're both integrated from minus infinity to infinity, we know right away that this guy is going to go to 0. So let me step back a bit just to remind you of a few things here. So an even function is a function that when you translate from x to minus x, the value of the function remains exactly the same. But an odd function is a function where you translate from x to minus x, the value of the function goes negative. So it goes from positive value to a negative value when you translate, excuse me. So what you see then is that for example, that cosine, just imagine a cosine function, and in this case it's cosine kx, so that's, with the translation from positive to negative x, that's going to be an even function. Whereas sine kx is going to be an odd function. And we see that this Gaussian function here, if you can imagine that, that's a Gaussian centered on 0. That's also an even function. All right, so what do we have? We have an even function multiplied times an even function. That gives you an even function. Here we have an even function multiplied times an odd function. That gives you an odd function. So an odd function integrated from minus infinity to infinity is going to go to 0. So we know that this function, this integral, is something we can throw away because that's going to go to 0, and we'll only have to focus on this one here. Okay. So this is what I just explained, and that this part is gone, and this is the integral that we have left to do. And so what I'm going to do is take this integral, and we're going to go to an integral table, and we see from our integral table that this is the relevant integral to do, which this is the generic result here. And you can see that in this integral, b in this integral is associated with 1/2 1 over sigma x squared. Okay, so that's the identity that we have to make here to take this integral, use this result to convert this integral into this result here. So that is the Fourier transform of the Gaussian function at some instant time equals 0, where it's centered on x equals 0. And this is what its decomposition is in terms of wave number given by this. Now we can look at this and you can see that this is just some numbers over here. This is the variance and this is the variance. But here's our variable now, k squared here. So it's e to the minus sigma x squared, k squared over 2. And that actually is effectively, looks like a Gaussian function too. So if I identify that x is equal to 1 over sigma k, where sigma k is the variance in k space, then you can see that integral can be written in this form, and it has exactly what you would expect for a Gaussian function, where we have minus 1/2 k squared over the variance here. All right, so in summary then, what we see is that in this particular case, we saw that the Fourier transform of a Gaussian-shaped wave function as a function of position gives us a wave function and a function of wave number, and that wave function actually has the same mathematical form. In other words, in this case, a Gaussian gave us a Gaussian. So we started out with a wave function that might look like this, and when we Fourier transformed it, we get a Gaussian function that looks like this, where now we're specifying them in terms of sigma x and sigma k, and sigma k is just 1 over sigma x. Now actually it turns out that the Gaussian, it's the only function actually that I know of that has the same analytical form after the Fourier transform. So if you take a Gaussian, you Fourier transform, you get back a Gaussian. But generally that is not true for any wave function that we're going to be working with. So when we're going to do these Fourier transform, you'll find that you might have some completely different type of function on one side compared to what you have on the other side. Now, let's go on then to our traveling wave packet. So we looked at the decomposition of the wave packet in terms of sinusoids at time equals 0. Then as that wave packet evolves in time, it's going to have this form then. So we have the original shape of the wave function, and then as it propagates forward in time, this is the time dependence here. And since we have all the different wave numbers or wavelengths present, then we have to sum them all up, and we get the final wave function here as a function of position. All right. So this expression then, the wave function as a function of position, is written as an integral of the wave function as a function of wave number multiplied times the time dependence for each particular wave number. Similarly, if we wanted to describe this the other way around, we could say if I know my wave function at time 0 in position space, I can describe its time dependence as a function of k and t by doing this integral here, by just expanding it out in terms of e to the minus I kx minus omega t times the original wave function at time 0, integrating over all values. In other words, we're summing up over all possible wavelengths to get the final wave function. Okay. Now, generally, you probably think more about, you like to think about a wave function moving through space. What we visualized was a wave function moving through space as a function of position and time. But it's equally valid to think about the wave function as moving in time as a function of wave number. Now, when the wave function argument is of the form of x minus vpt or x plus vpt, we learned earlier that that wave packet will not change shape as it moves forward in time. So remember that we put some definitions here. K times x plus or minus vpt becomes kx plus or minus omega t. So this wave packet remains unchanged in its shape only if omega over k, which is the wave speed, is identical for all wave numbers. Now, in what's called an ideal media, then that will be true. But in real media, we find that that's a little bit of an approximation. So we'll find that omega, if I rearrange this, omega is approximately equal to k times vp. So what happens then is the wave packet in real media may not move through space with the phase velocity that we talked about. It's actually going to move through space with something we're going to learn is called the group velocity. And also we'll learn that in this real media, as the wave packet moves through space, it might change shape. And so we'll go back to that, this sort of how this happens in real media, and this is what's called dispersion in the next later section here. Okay, so in terms of the Fourier transforms, one last thing I want to show you also is that we can do an identical transformation between time and frequency. So we just learned how to do a Fourier transform between the wave function as a function of position to a wave function as a function of wave number. So now what we're going to see is we can do a transform of a function with respect to time into a function with respect to frequency. And it's exactly the same integral, except now we're replacing k with omega and position with time, and this is the integral here. And then we have also the inverse Fourier transform, which looks like this, where notice there's the sign change on the e to the I omega t part. Okay. So we can even, if you wanted to, you could do a double Fourier transform. So you can say, do a double integral here, where you transform a wave function in terms of position and time into a wave function in terms of wave number and frequency. So again, these two representations of the wave function are perfectly equal. In other words, in the sense, equal in the sense that they have all the information of this function is contained in this function and vice versa. So there's no information loss in doing this transform, and you can equally describe the wave function in terms of this expression or in terms of this expression. So if you have an expression for this term or this wave function, both are equal ways of describing the wave function just in terms of a different basis. Here it's described in terms of wave number and frequency. Here it's described in terms of frequency and time. And similarly, of course, there's an inverse transform if you wanted to go backwards from the wave function as a function of position frequency to a function of position and time. All right. So that's it for this video. In the next video, we're going to look at something called the uncertainty principle for wave functions.